along with the 10 kilogram mass, how fast is the 10 kilogram mass going relative to me?
0.
And so it has an initial momentum of 0. This is in the -1 meter per second reference frame. And how fast does the 4 kilogram mass look like it's going? So moving to the left at 1 meter per second. How fast does this one look like it's coming at me?
7 meters per second.
Yep. And so my total initial momentum is 4 times 7, or 28 kilogram meters per second. So my total momentum is 28. Recognize when I shift reference frame, the math is really simple. If I'm moving at positive 6 meters per second, I just subtracted 6 here, and I got to that. When I'm at the -1, I subtracted -1, so 6 minus -1 is same as adding 1, and then -1 minus -1. So all I do is whatever my reference frame is, I just subtract that from what I start with, and I've got my new numbers. So if I were at a -2, well, 6 minus -2 is 8. -1 minus -2 is 1. So my momentums would be 32 and 10, or 42. So the secret to this technique is to get into a reference frame where the total momentum is 0. And that is a relatively simple calculation. So since when I move to a reference frame, I'm just subtracting how fast I'm going, so that's 6 minus v times 4, plus 10 times -1 minus v equals 0. So I'm trying to figure out what is the value of v that I subtract from both sides so that I end up with no momentum total. So I get 24 minus 4v minus 10 minus 10v equals 0. I have 14 minus 14v equals 0. 14 equals 14v. V equals 1. We can double check that. We've actually already confirmed that, but I'm not revealing quite yet how we've already confirmed it. So if I'm in a reference frame where I'm traveling at 1 meter per second positive to the right, oops, that got erased, so let's reinforce that. That means that this is going to look like it's going at 5 meters per second, which gives me a total momentum of 20 kilogram meters per second. This one was going at -1, and so now it's going to look like it's going -2 meters per second, which gives it a momentum of -20 kilogram meters per second, which gives me a total momentum of 0. So now I'm going to treat this like I'm in the 0 momentum frame. So before we get to that, where did we see this before? We've done this. It's been on the board. Matter of fact, somewhere around here, where we had 14 is equal to 14v.
Some more of that, before that.
Fourteen is equal to 14V. It would have been close to the first example we did after the car skidding problem. What was the situation where we had, end up with V equals 1, positive 1?
Perfectly inelastic.
Absolutely, and that's always gonna be the case. This is the answer to the perfectly inelastic collision final velocity. That is gonna be the zero momentum frame. All right, so here's the technique. We start out, so I got my 4 kilogram and my 10 kilogram in the lab frame. 0.6 and -1 meters per second. So, then I shift to the zero momentum frame, so I'm gonna subtract 1. I'm subtracting 1 because it's a 1 right there. And I'm subtracting it because, well, that's what I did right there. I did minus whatever that number is. So that puts me into the zero momentum frame. So now it's going 5 and -2. Then they collide. My total momentum is 0. Collision. I want to keep the exact same kinetic energy. I want to keep a total of 0 momentum. Badly worded. I want my total momentum to still be 0. What is a solution for how fast they're going for my final velocities after the collision so that my kinetic energy doesn't change and my momentum stays the same? Let me reword this. If I have a 3 kilogram mass going to the right at 2 meters per second, what is its kinetic energy? So 1/2 times 3 times 2 squared. Its velocity is 2 meters per second. What is another velocity that this 3 kilogram mass can go to get me the exact same energy?
-t.
Exactly. So I know that if all I do is just make this -5 and +2, my kinetic energy is not changing because my speed hasn't changed. Kinetic energy depends on speed. So I have the exact same speed, just opposite directions. In terms of momentum, I had momentum coming like this, the total momentum was 0, and all I've done is just flip them. My momentum is still 0. If this was in this new frame, it was 20, so I had 20 Descartes this way and 20 Descartes this way. Now I've got 20 Descartes that way and 20 Descartes that way, just by changing the direction that they're moving in. In the collision, they flip. I'm still in the zero momentum frame. And now I have to shift back. The final answer does need to be in the original reference frame, so shift back. Since I shifted the first time by subtracting 1, I shift back by doing the opposite. I add 1. And I get -4, and I get 3. And this is the lab frame again. And that's the answer. The 4 kilogram mass was going to -4 meters per second, and the 10 kilogram mass was going at 3 meters per second. So the first one has the advantage of, one of the solutions is the original problem, that they haven't collided. The second technique has the advantage of, you're not dealing with a quadratic, but you lose out on some information about, you don't get that immediate feedback of, oh, I did something right or wrong. And this one I feel is the easiest personally, because that's the most complicated math you do in the third technique. Whichever technique you choose, please learn how to do it. Please. I go through all these techniques in videos. So you have that, plus this will get eventually posted. So, and there will be a perfectly elastic collision, one-dimensional perfectly elastic collision problem on that last test. Guaranteed. And on that happy note, have a wonderful day. Have a nice weekend.